stuff behind the blockchains. I'm not going to really touch into that because that takes a lot of time and it's not actually central to the use cases for these technologies. So first thing, distributed ledger technology. So what is a distributed ledger? Essentially, it's just digital data that's shared and replicated over multiple locations. It's usually in a peer-to-peer network in some kind of overlay network, and usually it's consensus-based. So any kind of changes to the ledger, state changes, all the parties that are in this peer-to-peer network have to come to an agreement on how this ledger is updated and changed. And the most interesting implementation of distributed ledgers so far are blockchains. So when people hear blockchains, they usually think of the cryptocurrencies, which are the most popular implementation of blockchains. So things like Bitcoin, Litecoin, and even Dogecoin. So you can think of blockchains as essentially a ledger of transactions between different actors on the network. So, Alice gives, X amount of Bitcoin to Bob, and that transaction gets, enshrined in the blockchain. And that's how, you keep track of accounts and balances and things like that. Blockchains can exist both as public networks like Bitcoin and Litecoin, or as private networks, which are used for more special purpose things. And that's something that banks are looking at right now. And so, in our classical example, you can picture it like as this diagram. You can view a bank like this, or some kind of authority. Most CRUD apps on the internet kind of work like this, where you've got a bunch of actors, and they want to transact some state changes amongst themselves. And usually they have to operate through the mediation of some central authority. And so, there's some problems here. You got all your eggs in one basket. The central authority has control. You have to inherently trust this central authority. And, if something goes wrong, or if, there's suspicions, you have no real way most of the time to audit the central authority. And even if you do, it's usually difficult if you're, outside of the wire of that authority. And so enter blockchains. And blockchains, we've got this decentralized network. There's no single authority, and it's completely trustless. There usually exist consensus algorithms that define how changes to the blockchains are made. It's peer-to-peer, it's no single point of failure. Every actor on this network has the blockchain, a copy of the blockchain. So every actor can audit the blockchain themselves, audit all the transactions that have happened in its history. And the data on the blockchain is immutable. And this is achieved through the cryptography. And so whenever a block of transactions gets written to the blockchain, it can never be changed. You can only create new transactions. So in that sense, in our previous model, someone can, a sneaky person can go and edit a database row, and there might not even be a log entry for that, and you could never know it happened. Here that's actually impossible due to the implementation of how blockchains work. And blockchains also satisfy this thing called Byzantine fault tolerance, which we'll get into in a little bit later. So consensus, how does it work? So the most common form of consensus is proof of work. And that's where, if you've heard of Bitcoin mining, that's where that comes from. So the way it works is you want to, a bunch of transactions are in flight in this blockchain network, and you want to add them to a new block on that blockchain. What miners do is they essentially guess the hash of what this block will look like if it contains these transactions. And whenever a miner guesses the correct hash and it hashes to the correct set of transactions, that block gets added to the block. So it's a very hard problem that's hard to compute, and thus these miners actually guess at the solution, and that's why it's kind of called mining. But it's easily verifiable. So once a miner figures out the next block in the blockchain that encapsulates those transactions that were in flight, every other miner in the network can verify, oh, hey, yeah, that block kind of matches what we were expecting, and everyone agrees that this block will go on the blockchain. Proof of stake is a different way, where the people who are in charge of adding new blocks to the blockchain are actually the people who have the biggest stake in the blockchain. So if you can think of, if Bitcoin was, instead of having miners, it went with this proof of stake concept, the people who had the most Bitcoins would be the ones writing blocks to the blockchain. And the reasoning behind this is the people who are the most invested in a particular blockchain network are the ones who have the most incentive to keep it secure. And then there's some more interesting ones like proof of activity, which is actually a hybrid of the two, where miners create templates for the new blocks in the blockchain, and the people who have the largest stake actually kind of put their seal of approval on those templates. So Byzantine fault tolerance, you kind of have to talk about this if you're going to talk about blockchains. So Byzantine fault tolerance is when you see a system satisfies BFT, it tolerates a class of failure known as the Byzantine generals problem. And this kind of these classes of failures are the most general and generally the most difficult class of failures. And kind of like real world systems that kind of satisfy these are like, for example, like in fighter jets, when, fly-by-wire fighter jets, when a pilot makes some kind of adjustment on his, control surfaces in his cockpit, you'll have several redundant computer systems figuring out how to maneuver the airplane. And all these different computer systems have to come to a consensus on how to actually get the airplane to move. And they must satisfy this Byzantine fault tolerance property in order to make sure, the plane doesn't fall out of the sky. So, this is a real CS problem that's used in everyday critical systems. And this is kind of just a brief example of the actual Byzantine generals problem. You got a bunch of generals. They all need to agree whether or not they want to attack or retreat from a city. It's better that they do whatever agreement they come to. It's better that they all come to an agreement. So a half-hearted retreat or attack is worse than a full attack or a full retreat. They have to exchange messengers, and there could be traitors, generals amongst them. So you can kind of see how this kind of maps to computer systems quite easily, where you can consider generals different nodes in like a distributed network. You can consider the messengers, the messages between these different computer systems. And, traitors, generals can be considered, bad actors on that network, or even like faulty actors, like malfunctioning actors. And to kind of summarize what we have so far is we've got these blockchains, which are just an implementation of DLTs. They provide us with some really cool things, though, like security, immutability, fault tolerance, accounts, a bunch of other stuff like that. There's, different ways of achieving consensus that satisfies BFT. And, we've got public blockchains like Bitcoin, and we can even create private ones for some special use cases. So where do we go from here? Because, cryptocurrencies, are only so interesting. Is there anything cooler that we can do with blockchains? And the answer to that is yes. So enter Ethereum and smart contracts. And this is kind of the generalization of blockchains as a concept. So what is Ethereum? Ethereum is essentially, you take a blockchain or a blockchain implementation of a distributed ledger, and you actually pair it up with a decentralized computer. And so every node in the Ethereum network runs something called the Ethereum virtual machine. And what smart contracts are you can think of them as applications. And so every node in that network essentially runs or executes the smart contract, and they all have to come into agreement of the execution of that smart contract. So a smart contract is a computerized transaction protocol that executes the terms of a contract. Kind of interesting definition. Smart contracts that get deployed to the Ethereum network are visible to all users. And they're, in the case of Ethereum, they're Turing complete. So you can solve a lot of interesting problems using smart contracts. And like I mentioned just previously, every node on the network calculates the execution of a smart contract. And so in Ethereum, we have concepts like Ether and gas. So Ether is kind of like your analog to Bitcoin. Just like in Bitcoin and Ethereum, you have a currency called Ether, and you can transact that currency between different participants of this network. Now, gas is interesting. Every node is running this Ethereum virtual machine. What stops a user from basically uploading a smart contract that's got an infinite while loop in it? And that's where gas comes in. And so every operation on the Ethereum virtual machine actually costs a certain amount of gas. And you can convert Ether to gas using a simple computation where it's gas times the gas price. And the gas price is actually determined by the miners who are securing this network. And so here you can see how gas is calculated. So in the Ethereum virtual machine, these are kind of like the really low-level commands or execution that occurs. And you can see their associated gas cost. And there's even an API that you can call out to a contract and estimate, if I were to run this function on this contract, how much gas would I consume? And thus, how much Ether would I have to send in that transaction? And so DAPs, or decentralized applications, are kind of like these things taken to to their conclusion, where it's essentially an application that has a backend that's a smart contract or a series of smart contracts and a UI, like a web page. And the UI calls out to these smart contracts directly, and the smart contracts execute the business logic of your application. It's interesting too because you don't have to manage user IDs and accounts because it's all managed by the blockchain. And so you're essentially just, the UI allows you for a pass-through to the contracts in the back. And while it's inadvisable to store data on the blockchain, you can use technologies like IPFS, which stands for Interplanetary File System, which essentially stores pointers to where this data may live in this decentralized file system. And so some other quick things I want to mention is the reason for why private blockchains might exist is, you have specialized use cases, particularly banks are interested in this, where you don't want the kind of information that they're exchanging to sit in a public ledger. Also, you don't want to share the bandwidth of the network with the public. Right now, I think the Ethereum network processes 25 transactions per second, which is actually, fairly low if you want to do something like securities trading on it. And also by creating your own private blockchain, you can set the network difficulty. How easy is it to create new blocks, that sort of thing. Now, the tooling around all this stuff in writing smart contracts is actually quite good given how cutting edge this technology is. Solidity is kind of the main language that people write these contracts in, and we're going to go into a demo of that after this slide, or after these series of slides. There's some really good testing frameworks and frameworks for building and testing your smart contracts. One example is the Truffle Framework. Microsoft Azure even has blockchain as a service now as something that they provide, where through Microsoft Azure, you can provision your own private blockchains for whatever use you may have for it. And a lot of editors and IDEs now have support for both, Solidity, syntax highlighting, compiling the smart contracts and deploying them to either the public or a testnet blockchain. And there's a very popular JavaScript kind of library and API called Web3.js that a lot of people use for interacting and building these UIs for interacting with these smart contracts. And so, just to demonstrate, the people really do use this kind of Ethereum smart contract-based blockchain in the real world. So the Australian Stock Exchange actually later this year is going to be moving to a blockchain-based solution for handling their securities clearing and what's the term? It escapes me now. Does anyone remember the term when securities trade and the clearinghouse operates it? Settlements, that's what it is. So settlements are going to be done on the blockchain for the Australian Stock Exchange. Currently, settlements, in the real world, take anywhere from 2 days to like 30 days when you trade a security on a real world stock exchange, or on the blockchains, they'll be done in real time. Another interesting application of this technology is something called Slockit, where they're pairing the blockchain with Internet of Things devices. And so they're creating things like smart property, where you can have a storage locker that's connected to some Internet of Things based locking mechanism. And so you can trade access to these things over a blockchain. And people are even now implementing, or countries actually are looking into implementing land registries on the blockchain, because the immutability of this thing kind of really makes a lot of these things a lot easier, especially in the third world. And so for the demo that I'm going to take you through today, we're going to basically do a POC on a solution to a problem that we have in the real world, and it's kind of applicable to genomics. So one thing, if anyone's ever had to ask for controlled data or access to controlled data, they might be kind of familiar with this thing. So for us in ICGC, or if you want to use ICGC data, you have to have DACO approval. So the way that kind of works right now is, if you fill a form, the form gets sent to the DACO office. The DACO office approves that form, assuming they approve it. They check it off. And they enter that you're DACO approved in some central database. That database is then served by some ICGC API, and we in the ICGC DCC consume that API, do some more user level stuff, and then serve that through our own API. So there's actually several single points of failure, both the form, the paper form that you have to submit, the centralized DACO database, and even us in DCC, our database of our auth service that stores the user accounts. And so what usually happens, or not usually, but sometimes happens, is this, where stuff goes wrong. Gremlins eat the forms. You've got gerbils running around in your servers. Databases catch fire, wormholes happen, things like that. So this is like something that I feel is it's very ripe for a blockchain type solution. And a lot of people are doing provisioning of data access, or looking at doing provisioning of data access through some kind of blockchain mechanism. So that's what we're gonna do a proof of concept of that today. So so we're going to do this using two things. We're going to use something called test RPC, which you can install through Node, and essentially creates in-memory blockchain, like a test blockchain for you to work with. And it's Ethereum based. And the other thing we're going to use is this Truffle Framework, which allows you to quickly create, craft, and deploy contracts and do unit testing with Mocha and Shy, which happen to be my favorite test frameworks for JavaScript. And so let's get started on this. So the first thing, let's hide that, is you can. So I've got both Truffle and test RPC installed. So you can just invoke test RPC just like this. And so you get your available accounts. These are the accounts you can play with for testing purposes. The private keys behind these accounts, and if you can see that where this how to contact this guy. And so now let's make a new directory, OICR demo. And we can do something like this, truffle init. So we get some interesting stuff in here. So if I open this up in VS Code, we got a lot of free stuff in here. So we got a couple contracts that we can look at. So just so we have an idea of what the Solidity language looks like. We got some deployment scripts for deploying this to our test RPC, and a test folder where you can write your Mocha and Shy unit tests. So let's take a look at this MetaCoin contract. So this is what Solidity looks like. It may look slightly familiar and slightly alien at the same time. There's a lot of interesting things about this language. It's a shockingly low level, actually. So let's kind of go through this line by line. So this contract is called MetaCoin, and essentially it's a cryptocurrency that sits on top of another blockchain. So up here, this first line kind of defines what particular version of Solidity we're going to be using or compiling against. Here you can import, so one smart contract can actually be imported by another, and smart contracts can call each other. And even on the blockchain, you can have a deployed smart contract deploy a new smart contract calling another smart contract. So these things are like just chainable. And so here we define a mapping, and the mapping is of address to a number. And addresses on the Ethereum blockchain are essentially actors. So two things have addresses: real people who have real, wallets and accounts, and contracts. And we're saying this is a mapping of a person, so to speak, to a certain number, and that's going to be our balance. And this is our constructor, and we're saying, we're going to get into this a little bit later, but we're going to say whoever creates this contract is assigned 10,000 MetaCoin. And here we define some functions for how to transact these different these MetaCoins between different accounts. So what we're going to do is we're going to see if we can do a POC of a DACO replacement that's based on the blockchain. So we're going to author a new contract here, DACO. And I'm just going to copy this guy and empty him out. So we're going to call this guy DACO. We don't need that import because we're not going to do anything fancy. And we're just going to do this. And for now, function DACO, we're going to say it does nothing. No op. So what at essence are we trying to do in DACO? What we're trying to do is we're trying to determine if a user has access to controlled genomic data. So how are we going to address that? We're going to say, just remind me of the syntax here. Yeah, we're going to say a mapping from address to bool. So this is very simple, and we're just going to call this access. Is that the correct syntax? Sort of. And so what we're saying is we're going to assign, email. So we want to say someone's email is associated with DACO access, kind of like how we do it right now with the OAuth stuff. And so this is going to contain our mapping of authorized users or even users that have had their access revoked. So let's write a couple functions here. So the first function we're going to say is called grant access. And this function takes a string called an email, and it returns a bool. And it's going to be fairly simple. We're just going to say access for this particular email is now true. And let's return true to say this was a successful operation. We want to probably, write a getter. So we could say get access for a string. This returns a bool. And we're just going to say return whatever we know about this particular email. And of course, we want the functionality of revoking access. And what we want to say here is, you want to say access for this email is now false. And so for us to be able to compile and deploy this contract, we can do something like this. We can actually run truffle build. Or no, that's the wrong command. It's truffle compile. And so, what did I do? Returns. Cool. So our DACO smart contract is now compiled. We can see it here in the build directory, and this is what it looks like. So this is the ABI, the abstract binary interface. This is what we can call out to in this function, in this particular smart contract. And this is actually the bytecode that gets executed on the Ethereum virtual machine. So if we want to deploy this to our little test RPC network that we're running, we can modify this deploy contract script, and we can add our contract in here, facts.require, and we can say DACO.solidity. And we can say tell a deployer to deploy this contract. So the nice thing is, now that we've done this, if I go back to the Truffle command line here, if I can go Truffle migrate, and it's going to run that migration script, and it's actually going to deploy all our stuff to this in-memory test blockchain that we're running. And there you go. You can see it's deployed the DACO contract, and it's even assigned it an address. And you can see the transactions on the blockchain happen here. And so you can see, because this is just a test blockchain, every single transaction actually gets assigned to a new block, where in reality you could have thousands, I think. So let's actually interact with this contract that we just read. So we can do something called Truffle console. And so for JavaScript developers, this will be pretty familiar, because this is actually just really Node. And so we can do something like this. We got, auto completion. So we can see DACO, and then we can see if it's deployed. This is gives you like a promise. And we see it is deployed, it's got an address. And so what we want to do is we actually want to assign the instance of this deployed contract to a variable. So we can do like DACO deployed, and then we can say, something like instance DACO equals that particular instance. And so you see, we got it there, just to confirm. Yep. And so now if we try to operate on this smart contract, you can see we've got the functions that we've defined, grant the access, revoke the access, get the access. So let's actually grant an email DACO access. So we grant that access. foo@bar.org. And we get this receipt. And this is essentially the receipt for the transaction that just occurred on the blockchain. And we can compare it to what we see on our test blockchain here. And you can see, the gas usage for actually deploying this contract, or sorry, not deploying the contract, but actually assigning the value of true to that email took some gas. We can see what block number this particular transaction also occurred on. And you can see that kind of matches up here. So now let's verify that foo@bar.org actually does have access. So we can say, get access for that particular email. Now we get another receipt here, which is not so useful, and you might be wondering what's going on. And that's because whenever we're calling out to these functions like this, what we're implicitly doing is we're saying transaction, which you might not want to do in every case, right? So why do we need to add a transaction to the blockchain about getting a value where it doesn't mutate any state? And so the nice thing is, you can assume, this is not just a single node running a blockchain. This could be many nodes running on this blockchain. At any point, if any node is curious about any value or what any function call would do, rather than having to execute a transaction and spend ether and gas to execute that transaction, you can actually just call that function, just kind of personally on for yourself to see what would happen. And so we can actually say get access.call. So this doesn't actually modify the state of the blockchain. So no transaction is actually created that says, we're getting this access, but, we can see the value of this guy. And you get, true, which is what we set. Now, what happens if we do this? We give some bogus value. In a lot of languages, you'll get like, a null pointer exception or a segmentation fault or something like that. So we're just going to hit this and we get false. The reason this happens is the way Solidity handles mappings like this. In Solidity, all mappings are virtually initialized for every possible value of their key. And the default value for bools will be false, for numbers will be 0, for strings will be empty, that kind of thing. So you'll never run into kind of like a null pointer exception or like a none type or anything like that. And then just to confirm that this is working, we can do something like revoke access. Probably don't want to call that actually. Probably actually want to transact that on the network. We get the transaction log here, it occurred here. And we can now call to see if this guy really did get his access revoked. And you can see that. Now, with this smart contract, there's a very big flaw in what we did. And it's the fact that anyone who knows about this smart contract can change the state of this smart contract, which is not so good. That kind of defeats the whole purpose of DACO. You only want certain people to be able to actually, grant access. So what we want to do is we want to actually create some kind of admin address. And in the creation or in the constructor of our smart contract, we want to do something like this, transaction.origin. And before granting access, we want to do something like this. We want to see if the message sender is equal to the admin. Only then do we actually want to execute the smart contract. And of course, if this doesn't work, we return false. You're not the admin. You're not allowed to modify someone's DACO access. Now, I used two different things here. I used a message.sender and a transaction.origin. And there's a reason for that. So assume we've got some kind of call chain like this, B, C, D. So for transaction.origin, so we can say D is us. You can see D is, let's say, just call it DACO. DACO is this contract. For the transaction.origin, what we would get is A, the address of A. And that's because, smart contracts can't act out on their own. They can't reach out on their own. And so for the origin of every transaction has to be like an end user and their particular address. Where here we're more interested in whoever called out to this particular guy. So DACO. So the message.sender for us in this case would be C if the call chain was like this. And so there's interesting use cases for doing things like this because you can orchestrate it so you got multiple contracts talking to each other to produce some kind of output or state or whatever. And so obviously we would kind of wrap this, check around all our stuff, and that's our POC right there for implementing a very simple kind of version of DACO, but on the blockchain. And what would be interesting is if we go back to that slide I had, you could imagine we could get away with removing a lot of these different nodes. The form filled by a user could actually just be a UI that talks to, a smart contract on the blockchain that basically just stores requests for DACO access. The DACO office could have a UI that then grants that request, and that request then gets sent off to another smart contract. And the ICGC and GCC APIs could just all be reading off of the blockchain, checking to see, what someone's DACO is like. And the nice thing is both like, a web server running the UI, both a server or a node in the DACO office and a server and node running here, we're now decentralized. We got 3 people or 3 different locations that all have a copy of this, this ledger or this blockchain. And, there's no more single point of failures, and, you won't get things like this. So one last thing I want to take you through is actually how to provision your own blockchain. So you're kind of interested in this. You want to play with your own blockchain. You don't want to run on the Ethereum network. You don't want to pay real money to create transactions. So I actually had a Docker container to show you guys how to do this. But the problem was, I don't know if you guys are aware, but Amazon S3 is currently losing its mind, and Docker Hub has a DDoS on their registry. So we're going to hope this works, because I have to kind of sort of re-implement this real quick. So let me actually don't save. So to create your own blockchain, you have to start with something called a Genesis block. So this is the first block that gets written to your blockchain, and it kind of looks like this. And this is where you define some parameters about your blockchain. So you can set the gas limit for execution. You can set how hard it is to mine new blocks, and you can even allocate or pre-allocate accounts with a certain amount of ether. So you want to. This is particularly useful if you want to set up a private chain and then you want to already have the funds for users to start transacting with one another. And I've put this on GitHub, so you guys can build this Docker file yourself. Or once Docker Hub comes back online, you can actually run this, and you can walk into this container and you can actually execute this. So that's what we're going to do. So I'm going to quickly Docker. So the two steps for doing this are, you want to actually initialize a new blockchain. So you provide it with a data directory where your blockchain data is actually going to live, and you provide it with that Genesis block I just showed you. And then you actually, I should step back for a second. Geth is one particular implementation of an Ethereum node. There are other ones. This one's written in Go. There's a C++ one, and I believe there's even a Python one. The Python one, they don't recommend using in production, but it's actually great for understanding how the protocols in the backend work, because it's written in a way that's really easy to read. So we're going to actually fire up this private blockchain. And so we're going to... And I've just started my own Ethereum private blockchain. I've called it OICR. I've assigned it some values. The very important thing here is I've changed the network ID. That's because if you don't change this guy, you're going to try and connect to the production real live Ethereum network. And just to show you, this guy really is working, this particular blockchain. If I go here, so I've downloaded something called Mist. It's like an Ethereum wallet / contract browser. And I can execute the command to start it. And I can actually tell it, hey, don't go to the real live Ethereum blockchain. Go talk to this private one I've got running instead. Warns me about an insecure connection because it's HTTP. And there, it's running. And you can see I've got some ether. And so, right now this ether number is not moving because we're not actually mining on the Ethereum node that I've got running. So we should probably mine, because we want transactions to be processed. So I started the console here. This is also kind of very node-like. So I can do something like miner.start. And so this miner is going to start mining new blocks. And any second now, you'll see blocks start getting added to the blockchain. So the Ethereum blockchain is designed that I think every 12 to 15 seconds, a new block gets added. Here it's happening, much faster because I lowered the network difficulty in the Genesis block. And so you can see new blocks are being mined. And if we go to my Ethereum wallet, you can see my balance is being updated. So I don't know if anyone wants to buy some ether, you can get on the ground floor right here. This kind of Mist wallet, we could also deploy the contract that we had. So if I open up my the one I know that works, we could do something interesting like this. We could take that bytecode that we generated from our DACO contract, and we can say, hey, deploy this contract for me. And you can just dump that in here and be like, I don't know how much ether I'm going to send. 100, it's probably a lot. And deploy. I actually don't remember the password I set for this demo account, so you'll have to take my word for that this is going to work. You can also, inside of this guy, this guy's pretty useful actually for debugging contracts, because in addition to deploying a contract, you can then, if you know the address of a contract, let me click on this guy, you can actually watch that contract. And so you can pass in the address for that contract. And if you know that ABI that you saw in here, you can actually copy paste this guy in here. So the Ethereum wallet here or the Mist wallet actually, you can start modifying the contract straight out of this wallet. So it's pretty useful. The tooling around this is actually pretty remarkable given how cutting edge this is. And yeah, I think that's all I got to show. Any questions? Maybe give him a mic.
I would love to see some of the contracts that people have already written. Are there any that are currently in production?
So going back to those DAP things that I was mentioning, there is actually an amazing website where you can go explore all the DAPs that people have created that are running on the Ethereum network right now. And it's called State of the DAPs. And actually with this D, it's kind of JAPs. I've heard people pronounce it JAP or DAP or JAP. But these are all different smart contract based applications that people have written. I saw a very cool one, which was if you've ever played the video game or kind of something similar to it called Civilization, where I've seen someone write a DAP that was basically that game, except when you lost your units in that game, you would actually lose real ether, therefore real money. Which I don't know, I wouldn't play that, but yeah, you can check this site out. You can see quite a lot of activity. Sorry? I have no idea what the colors mean, to be honest. But let's say we can just click on one, pray for prey, I don't know. Keep in mind, I don't actually have a real Ethereum wallet on this computer, so I probably won't be able to interact with these. So you can see people are actually creating these games, and it seems something related to buying fish. Pretty cool. Anything else? Yep.
So I just have sort of a technical question. Why did you pick the technology you picked? Like, why the JavaScript? Why these libraries?
Well, it's a good question, actually. So let's go to the Truffle Framework. So the Truffle Framework is actually built by these guys called Consensus, and they are the people behind blockchains and particularly Ethereum. They come up with the best tools that are available for working with these kinds of things. And, Microsoft even works with these guys for like implementing their solutions inside of Visual Studio. So you can do cool things. So these guys, I think, have created a plugin for Visual Studio that you can, where you can actually, author your smart contracts inside of Visual Studio and with a click of a button, deploy them to some blockchain as a service or something like that. And so anything that these guys write, you'll tend to use. And I've played with a bunch of other, frameworks. And this one was quite honestly the easiest. And since a lot of the DAPs that you end up writing are going to be just like some kind of JavaScript single page applications that are going to be talking to a smart contract, it actually makes a lot of sense to keep all your tooling in the JavaScript kind of world.
So is Ethereum like Bitcoin? So when you say one Bitcoin, is it like one Ethereum?
So Sid asked, is Ethereum like Bitcoin? Is like one Ethereum like one Bitcoin? And so that's a good question. Ethereum is traded just like Bitcoin, so Ether, I was mentioning. You can consider it its own cryptocurrency, and it's kind of used as payment for running the network. Where's my Mist wallet? Well, I was going to show you, but in the Mist wallet, where it said like I had X amount of Ether, you can actually, there's a drop down. You can see what is this amount of Ether worth in Bitcoin, or what is it worth in US dollars and that kind of thing. And so there are exchanges, just like you can trade Bitcoin for real money and real money for Bitcoin. You can trade real money for Ether, vice versa. You can trade Ether for Bitcoin, that kind of thing.
Do you suggest mining it?
Sorry?
Do you suggest mining it?
No, I do not suggest mining it. I know lots of people that do, but personally, I wouldn't suggest mining it, no. That said, there exists these things called mining pools. You can join a mining pool, contribute your hashing power, and you'll get some stuff out of that. But if you want to mine on your own, you're not going to get anything.
So I know you didn't want to go into technical detail, but the Byzantine generals problem, could you talk a little bit about how like this tackles it? Like, does the network shut down if there's like too many road actors, or
Yeah.
maybe elaborate on?
So the question was elaborating on the Byzantine generals problem. So it really comes down to the only way to break the network is 50% plus one, right? So if the majority of your network are bad actors, you're in trouble, right?
Okay.
And so the kind of the Byzantine fault tolerance comes out of the fact that, if we're talking about the generals, is that all the loyal generals have to come to some kind of agreement. And if you've got more disloyal generals than you have loyal generals, the network is broken. I don't know if that kind of.
Yeah, that approaches it. Then
Yeah.
Is there like degradation in performance as you approach that point, or is it?
Yeah, there might be, because what happens is, like, let's say you've got a coordinated set of like bad actors. They can start creating their own kind of like branch off that blockchain. And yeah, this is fairly technical. I'm not sure, but I imagine there would be, because even with multiple good actors, let me bring that back up. You can have two miners at the same time discover a block, and then the nearby nodes might assume that, some nodes might assume one miner is correct, and some miners might assume another node is correct. Eventually, the consensus algorithm will solve that. One miner will, in the Ethereum case, the miner that in particular that gets chosen as the new block gets a reward, and the miner that didn't get chosen gets like a semi-reward. They're called uncle blocks. In Bitcoin, they're called orphan blocks. Those miners in Bitcoin don't get any reward. And so there is some cost associated to the network in general with doing this. And so, yeah, if the more bad actors creating more or attempting to create these bad blocks would probably bog the network down, especially if they're dumping even more transactions onto the network.
Is there some sort of time limit on convergence? They're trying to come to a consensus. Back and forth.
Yeah, so the question was, is there some kind of convergence or time limit on coming to a consensus? And yeah, so as I mentioned earlier, the network in Ethereum's case is designed to generate a new block every, I think, 12 or 15 seconds, something like that. And so if there is trouble on the network and things are taking too long to be generated, the network will actually lower the difficulty, the hashing difficulty of creating that next block. And then so the network self-regulates the difficulty of creating new blocks. And just kind of to touch on that, what's interesting is a lot of these companies that are working on private blockchain solutions are getting rid of the concept of mining and gas and things like that, because in the sense that where your blockchain is actually a series of banks communicating to each other on a public ledger, you don't need a trustless system, because the banks are going to assume, I assume they're going to trust each other. And so in that sense, you don't need to worry about, payment and gas, because in general, the banks are going to be nice to one another. So there's that concept as well.